In this video, we want to learn about electromagnetic induction. Learning outcomes. At the end of this video, you will know what electromagnetic induction is all about, Faraday's law of electromagnetic induction, Lenz's law, Fleming's right-hand rule, electric motor and generator, working principle of D.C. and A.C. generators, and working principle of an electric motor. What is electromagnetic induction? It is the phenomenon of inducing an e.m.f. in a circuit by a changing magnetic flux. This was observed by an English scientist called Michael Faraday in 1831. He observed the relationship between a changing magnetic field and the electric field created by the change. This is what he observed. He had a coil connected to a galvanometer and a bar magnet. While pushing in the bar magnet into the coil towards the coil, he observed a deflection on the galvanometer. And as we all know, a galvanometer is a device used to detect the presence of current and also the direction in which the current is flowing. So in moving the bar magnet towards the coil, the galvanometer was deflected in opposite direction to the bar magnet. He tried to remove it back, and the galvanometer equally deflected in opposite direction. The deflection indicates the presence of current, then the direction shows how the current is flowing, which is opposite to the motion. He equally kept the bar magnet constant, moving the coil, and at each point, current was induced. So, when he kept the bar magnet stationary and the coil stationary as well, the galvanometer does not deflect, showing there was no presence of current. So, current was induced when there is a motion of either the bar magnet keeping the coil stationary or the coil keeping the bar magnet. After this experiment, he came up with two laws, which we call Faraday's law of electromagnetic induction. This is just the demonstration of the law. Let's look at what the law states. He had two laws. Two laws were developed. Faraday's first law of electromagnetic induction states that whenever there is a change in the magnetic flux linked with a circuit, an e.m.f. is induced in the circuit. Like we just saw, whenever there is a movement, either the coil or the bar magnet, current is induced. Let's look at the second one. Faraday's second law of electromagnetic induction states that the induced e.m.f. in the circuit, the direction of the induced e.m.f. is directly proportional to the rate of change of the magnetic flux linking the circuit. Mathematically, Faraday's law is expressed as equation 1, that the induced e.m.f. is equal to the rate of the magnetic flux. The negative sign here shows the direction of the induced e.m.f., like we just observed. Then we also have Lenz's law. He came up with another observation, and Lenz's law of electromagnetic induction states that the direction of induced e.m.f. in a conductor is in the direction which opposes the change of the magnetic flux. According to him, as earlier stated, as the bar magnet was moved in, there was deflection in opposite direction, giving rise to the negative sign we saw earlier in the mathematical expression. And when the coil is being pulled out, there was also a deflection. This deflection, represented by the negative sign, is what was observed by Lenz's law. That yes, if there is a movement of a bar magnet keeping the coil constant, or the coil keeping a bar magnet constant, current is induced. But the direction is opposite to that of the bar magnet or the coil, as the case may be. To the direction of the induced EMF is given by Fleming's right hand rule. Let's look at it. That if you stretch out the right hand, that if the thumb represents the motion of the bar magnet or the coil, the first finger represents the magnetic field, then the second finger will represent the induced EMF. So according to Fleming, that if you stretch out the right hand such that the thumb, the first finger, the second finger are perpendicular to each other, then the motion of the motion is represented by the thumb, the field, magnetic field by the first finger, and the induced EMF by the second finger. So this helps us to easily remember the relationship between the motion, the magnetic field, and the induced EMF. Let's look at factors that affect the induced EMF. We have the number of turns in the coil. As we can see, a coil with a higher number of turns induce more EMF than the one with lesser number. The strength of the magnet, a magnet with higher strength, induce more EMF than the one with a lesser strength. Then the speed with which the magnet, the speed of the motion, if the speed is very fast, the induced EMF will also be much. So these are the factors that affect the induced EMF. Let's look at electric motor and generator. A device that converts electric energy into mechanical energy or mechanical energy into electrical energy, we call it a dynamo. And when a dynamo changes electrical energy into mechanical energy, it is called an electric motor. So an electric motor is a device that converts electrical energy into mechanical energy. Then we also have a generator. When a dynamo changes mechanical energy into electrical energy, we have a generator. And there are two classes of generator. We have the alternating current or the AC generator, and we have the direct current or the DC generator. And both AC and DC generator operate on the fundamental principle of electromagnetic induction. Let's look at the working principle of AC generator and DC generator. This is a diagram of an AC generator, consists of bar magnet, coil, slip ring, carbon brush. So, how does it work? As the coil rotates in the magnetic field, through the coil changes and therefore induce an EMF between the end of the coil. When this coil is placed here, we say a generator converts mechanical energy into an electrical energy. So as the coil rotates, the mechanical energy is being converted into electrical energy. As it rotates, it cuts through the magnetic flux, and the slip ring allows the transfer of the alternating EMF induced in the rotating coil to the external circuit. And the induced EMF is maximum when the coil is parallel, like we have here, to the magnetic line of force, but it is zero when it is perpendicular to it. So, as the coil rotates, it cuts through the magnetic flux. And according to Faraday's law, we say whenever there is a change in the magnetic flux, e.m.f is induced. So as the coil rotates, it changes the magnetic flux produced by the bar magnet. So this is the working principle of an AC generator. Then let's look at the working principle of a DC generator. The setup is similar. You have your bar magnet, you have your coil, the brush, then slip ring commutator. So how does it work? A DC generator using the same principle like AC generator, the coil is mechanically rotated to cut the external magnetic field, and an e.m.f is induced. Unlike the AC generator, the end of the coil are connected to slip ring, which is connected to the brush. And the brush and the slip ring rectify the induced EMF and ensure that the current flows in the same direction. So DC is produced by a DC generator, and this is direct current that flow in one direction, while AC alternating current that varies periodically. In one of our videos, we looked at alternating current circuit, so you can check to get more information about alternating current. So a DC generator produces a DC current. Let's look at the differences between AC generator and DC generator. There are several differences. AC generator converts mechanical energy into alternating current, while DC converts mechanical energy into direct current. The structure of AC generator is simple, while that of DC is a complex one. The current in AC generator flow reversal periodically, while in the case of DC, it flows only in one direction. AC generator, AC is classified into single phase, three phase, synchronous and induction generator, while DC generator is classified into separately excited and self-excited generator. AC generator generate high voltage output, while DC generator generate low voltage output. AC generator has no commutator, while DC generator uses commutator to maintain unidirectional current flow. AC generator more expensive than DC generator. AC generator is highly efficient due to smooth slip ring, while DC generator is less efficient because of commutator and brushes that wear out quickly. AC generator has lower risk of short circuit due to efficient brushes, while higher risk of short circuit due to wear and tear of commutator and brushes are observed in DC generator. AC generator has aperture, which is always the rotor, while DC generator has aperture, which can either be the stator or the rotor. Low maintenance is required for AC generator, while DC generator require frequent maintenance. Output can be easily transmitted using transformer, can be step up or step down, while DC is difficult to transmit output due to the absence of transformer. This AC generator uses transformer, while a DC generator does not use transformer. Current is induced in either the stator or the rotor, while current in AC generator, while in DC, current is induced in the rotor only. AC generator used in home appliances, micro motors, among others, while DC generator is used for large electric motor. So let's look at the working principle of an electric motor. Like we earlier stated, electric motor convert electrical energy into mechanical energy. So as we can see here, you have a bar magnet and you have a coil connected to a load, connected to an electric current. When a rectangular coil, as we observe here, is placed in the magnetic field and current is passed into it, a force acts on the coil, which rotates it continuously. And in that process, rotational mechanical energy is being produced. So the current supply to the coil in the magnetic field causes it to rotate, producing rotational mechanical energy. So this is the working principle of an electric motor. We have different types of electric motor. We have the DC electric motor, which is powered by DC current sources like battery. We have AC motor powered by alternating current sources like electrical grid. Let's look at devices that make use of electric motor. Electric motors are used to power many devices used in everyday life, like refrigerator, washing machine, elevators, ventilation fan, among others. Even in industry, bulk materials handling pump, rock crushers, machinery operation, compressors, among others, also used electric motor. Thank you very much for listening. Please subscribe to my channel for more videos. Like and share this video. Bye for now.